Hey, students, guess what time it is? It's science time. Get out your notes and let's start learning. So next question. A ball is thrown at a velocity of 50 meters per second at an angle of 30 degrees from the horizontal. What is the range of the ball? What is the maximum height of the ball? How long does this ball spin in the air? And again, we're ignoring wind resistance. So what I'm going to do is get the problem set up, and then after I get set up, I'm going to have you solve for the different parts in several increments. So let's go ahead and get this one started. All right, so let's go ahead and work out this next problem. And so the way we start off is with a diagram. So the story is we have a projectile. So here is our ground. And we're just using a ball here as the projectile. And it's being launched at 50 meters per second at a 30-degree angle above the horizontal. So the question is that when it's flying through the air, we want to know what is the highest point. So that's the distance in the y direction. What is its range? That's the distance in the x direction. And also at what time will it land? Now obviously that's not quite drawn correctly here, but this should be a parabolic curve, but hopefully you get the idea. So again, so the ball is being shot at 50 meters per second at a 30-degree angle above the horizontal. We want to know what is the highest point it will rise, which should be halfway through its flight. What is its total range? So assuming that we're shooting it from the ground and it's landing back on the ground, so there's no change in its elevation. So what is this range? And then also at what time will it land over here? Now, if you remember with the last one, we had one where it was on a cliff and it was being launched horizontally, and we treated it as though an object was falling straight down. This part, we're going to have to work this one out a little bit more, because if you look at this projectile, it's actually moving in two different directions. And if you remember from a while back, if it's moving at a 30-degree angle, it's actually moving in two different directions. It's moving horizontally and it's also moving vertically. So what we need to do first is break this down into its x and y components. So we're going right back to vectors again. I know you guys are thrilled about that. So before we start answering these questions, we need to break this down into its two component directions. So let me redraw this. We have a projectile at 50 meters per second, and it's 30 degrees above the horizontal. So what we need to do is break this down into its x and y components. So what is the velocity in the x direction, and what is the velocity in the y direction? And we have a right angle triangle. So the 50 meters per second, that's actually the resultant of this x and y direction. So what I'd like for you to do is I would like for you to go ahead and solve for the velocity in the x and the velocity in the y direction. Okay, so just a quick little recap. 50 meters per second, that is your hypotenuse. V sub x, your velocity in the x direction. This is your 30-degree angle. This is your adjacent. This side right here, which is the same thing as your Vy over here. This is your opposite, and this is your hypotenuse. Okay, so solve for your Vx and solve for your Vy. Now hopefully you did well on that part. So let's go ahead and work this one out. Alright, so what we're going to do is, let's go ahead and solve for, let's say, the Vx here first. So you have your adjacent and hypotenuse. So adjacent and hypotenuse, you're going to be using cosine. So cosine theta is equal to the adjacent over hypotenuse. So the cosine of theta, which is going to be your 30 degrees, is equal to your adjacent. Your adjacent is v sub x, and the hypotenuse is your 50 meters per second. So we need to rearrange this, so we solve for v sub x. So Vx is going to be equal to, when you get rid of the 50 meters per second, so we have to multiply both sides by 50 meters per second. So you get 50 meters per second times the cosine of 30 degrees. Now make sure that your calculator is in degree mode. That would be helpful here. So if you take the cosine of 30 and multiply it to 50 meters per second, you should get about 43.3 meters per second. And what I would recommend doing is label your diagram. This is traveling at 43.3 meters per second horizontally. Now, to solve for the v of y. V of y is your opposite. So SOHCAHTOA, that's your sine theta, is equal to your opposite over hypotenuse. So the sine of 30 degrees, your opposite is v sub y. Your hypotenuse is 50 meters per second. Alright, so when you solve for v sub y, 50 meters per second is in the denominator, so we need to bring it up to the top, so you want to multiply both sides by 50 meters per second. So Vy is equal to 50 meters per second times the sine of 30 degrees. So V sub y comes out to be 25 meters per second. So sine of 30 is 0.5 times 50 is 25. So vertically, this is going to be traveling at 25 meters per second. Now, since we have these two velocities here, we have the velocity in the y direction, and we have the velocity in the x direction. This 30 degrees and 50 meters per second doesn't matter anymore. What's most important are these two velocities now. Okay, so we're going to be using this information, the velocity in the y, the velocity in the x, to solve for our values in the y and the x, and also with our time. So this is going back to the previous problem where the projectile is being thrown off of an edge of a cliff horizontally. So now we're kind of going back what we were doing before. So I'm going to redraw this with some of the new details. So again, we have, bring this down here. So now what we have is the velocity horizontally is 43.3 meters per second. Vertically is traveling at 25 meters per second. Okay, and then from that, we want to know what is the highest point, d sub y. What is its range, which is d sub x. And at what time will it land? Okay, we need to find those bits of information here. So if you remember with the previous problem, or even with projectiles in general, is that horizontally they always travel at the same speed. Okay, so throughout this entire flight, this horizontal velocity will always remain at 43.3 meters per second, ignoring wind resistance. This, so if you ignore this part of it, we have the 25 meters per second going straight up. Treat this as though you're throwing a ball straight up in the air, 25 meters per second. Because the path of this ball is actually the resultant of those two. So it's acting as though you're tossing a ball straight up in the air, 25 meters per second. And it's also acting as though you're rolling a ball across a level ground at 43.3 meters per second. Okay, so we need to break this down into our givens. But we want the givens in the x direction and also all the givens in the y direction. I don't need that there. Okay, so in the x direction, what do we know? Well, so only look at this part right here. So anything going across horizontally. So the only thing we have here is this value here, which is your v sub x. So v sub x is 43.3 meters per second. Is there anything else acting in the x direction? So you know this. It's d sub x. But we don't know what that value is. Is there anything else acting in the x direction? And not technically, but there is one thing, and it doesn't matter whether it's in the x and y, it's time. Okay, now I'm going to talk a little bit more about time here a little bit. Okay, so we also will need that information. So if you notice here with horizontal, we only have one bit of information and we have two unknowns. We can't do anything quite yet. Now for the y direction, we have a little bit more details about it. So it's initial, so when you look at this, the only information we have is 25 meters per second going straight up. So that's your d sub y. But that's also the point where it's being treated as though an object is being thrown upward. So that is, oh, I'm sorry, not d sub y. First I want to talk about v sub y. I'm sorry about that. So v sub y, see, this is the reason why you label your diagrams here. V sub y is 25 meters per second. Okay? And so it's being thrown up at 25 meters per second. But that is your initial velocity. Okay? So, treat it, if you're throwing an object upward at 25 meters per second, it's going to go up, it's going to slow down as it goes up here. Eventually it's going to reach a point where its final velocity up here at the top will become 0. So that, vertically speaking, will be here, vertically. So it's Vy final will be 0 meters per second. Now, if you look at the flight, where would that take place? That should be taking place up here, in the halfway point. Now, on the way back down, if you remember, it's going up at 25 meters per second. Right before it hits the ground, it should be going 25 meters per second vertically downward. Anything else acting in the y direction? Well, we have d sub y, which we don't know. So that's the highest point that the ball will reach. Is there anything else acting in the y direction? Hopefully remember my good friend gravity, or the acceleration of gravity, so A or G. Oops, sorry. That helps if I bring it into view here. So we have A or G here, which is going to be 9.8 meters per second squared. But because this is being thrown straight upward, this is going to be negative 9.8 meters per second squared. Okay, and is there anything else also acting in the y direction here? Well, just like over here, we have time, but actually, when does it reach 0 meters per second? It should be here, not here. So what I'm going to do, I'm going to label this as T 1/2. And the reason why I'm doing that is because that's its half time. So halfway through its flight, its time should be here. The other half of its flight should be a mirror image of it. So we need to know what is its half time. But this time over here is going to be its total time. So we also need T total. So technically we're solving for its total time in the air, which also means over here on the X direction, we want to know when it lands over here, which is its total time. So if you end up just using the time when it reaches 0 meters per second here, then what we would have solved for was what is the range when it reaches the highest peak. We would not have taken into account the full duration of its flight. So that for the calculation is going from 25 to 0. And the time that we get when it reaches that point up here, so when it reaches this point up here, is technically halfway through its flight. But then it's going to take the same amount of time for it to also fall back down. So again, this is like the ball being thrown upward at 25 meters per second, slowing down, slow down, slow down. Its final velocity here is 0 meters per second, and we'll get the time. But then we also want the time as it falls back down. So it's going to go, the final velocity at the highest point is going to be 0, but then it's like it's starting all over again, where its initial velocity becomes 0. It's going to speed up, speed up, speed up, so it's going to be positive 9.8 meters per second as it's falling back down. And it's going to take double the amount of time for it to go up and come back down. So whatever you have here, you have to double it to find out what time will it land. Alright, so let's start with the equations that you'll be needing. The equations for the horizontal direction, there's really only one form that you'll need here. That is the velocity is equal to distance divided by time. And we're looking at the velocity in the x direction and the distance in the x direction. And the time that we need is its total time. Now, for over here, what you're going to have to do here is there's several different formulas that you can use for this one. One of them is Vf is equal to Vi plus At. The other possible form you could be using is Vf is equal to the square root of Vi squared plus 2Ad. And the other one is D is equal to Vit plus 1/2 At squared. So, one thing I would recommend doing is the time is going to be the same time here. So time doesn't matter, it's not a vector, it's a scalar unit, so it can be applied to either one. Solve for your time first. Treat this as though you're tossing a ball straight up in the air. And solve for at what time when it reaches its highest point. And when you have that highest point, that's what you're going to be putting down here. Oops. When you solve for your time, that's what you're going to be putting down here. And then, once you have your time, you can go ahead and solve for your distance in the y direction. And that will give you the highest point that will be acting here. So, the distance that you see in the formulas down here are all going to be distance in the y direction. So all of these are only for the y direction. All of this is only for the x direction. So the time that you get here, what you have to do is to find the total time for it to land, is you're going to have to double it. So you're going to have to multiply this value, you have to multiply this value here by 2. And whatever value you get here is also the same value that you're going to be putting over here as well. Okay. Once you have that time, then you go ahead and plug that into your distance, and that will give you the range in which the ball would have traveled. All right. So again, solve for the time half, and solve for the distance in the y direction using these formulas down here. Once you get your time, double it. That's the time that's going to land. Once you have that value, that's what you're going to be putting over here, and plug that into this equation to solve for what is the range, the distance in the x direction. So go ahead and work those out and select your answers. Now the answers may not be exactly what you got, but pick the one that's closest to yours. And then I will go through and show you how to work this out. All right. If you have any questions, email me, and good luck. All right, so hopefully you did well on answering those questions, and let's go ahead and work this problem out. I get a clean piece of paper. All right, so let's start with the y direction. Okay. So starting off with, let's first solve for time. So in the y direction, let's get this centered here. So in the y direction, we're going to be using, sometimes you can do this one different way here, but pick the one that, try to use one where you're actually using the variables already given to you. So I'm going to go with, right now, EF is equal to VI plus AT. I'm going to use this to solve for time. So if I rearrange it, I need to subtract VI. So I end up with VF minus VI is equal to AT. And then I need to divide out the acceleration. And I come up with the formula of T is equal to VF minus VI all over A. I'm going to plug in the values. Time is equal to the final velocity. So this is the final velocity when it reaches the highest point vertically, which is going to be 0 meters per second. So the time is going to be, the final velocity is 0 meters per second. Its initial velocity was being thrown up at 25 meters per second. And since it's going up against gravity, it's going to be slowing down, so it's going to be decelerating at negative 9.8 meters per second squared. And when you work this out, the meters will cancel out, seconds, one of the seconds will cancel out. You have 1 over 1 per second, which will give you a value of seconds, and I end up getting a value of about 2.55 seconds. So that is the time when we reach this point up here, 2.55 seconds. So in the problem, the time will be 2.55 seconds. Now the total time, because it's going to take 2.55 seconds for it to reach the highest point, another 2.55 seconds for it to come back down. So I need to double that time, and if I take 2.55 multiplied by 2, I'll get a time of 5.1 seconds. And that is the time also over here, 5.1 seconds. So now, let's go ahead, while we're still working in the y direction, let's find out how high will this go up. Okay, so I want to find this value here. So now there could be, again, more than one way of doing it here, but try to use the ones where you're using the variables that were given to you. So what I'm going to do is VF is equal to square root VI squared plus 2AD. And so I need to rearrange this, so I'm solving for the distance. So I need to square both sides. So I get BF squared is equal to BI squared plus 2AD. Since this is being added, the BF squared is being added to this, I need to subtract it out. So I end up with BF squared minus BI squared is equal to 2AD. And since 2A is being multiplied to D, I need to divide those two out. And I end up getting D is equal to BF squared minus BI squared all over 2A. Okay, so now I'm going to plug in the values into it. And again, we're treating this as though it's a projectile where it's being thrown straight up into the air. Alright, so its final velocity when it reaches the highest point is 0 meters per second. And I'm going to square that. Its initial velocity is 25 meters per second. And you square that as well. All over 2 times, and since it's being thrown upward, its acceleration is going to be negative. 2 times negative 9.8 meters per second squared. So the distance. Now, a couple of common mistakes a lot of people make when they're doing this. Now this part right here, as you can see, 0 meters per second being squared, that doesn't matter here. We can ignore that. One common area where a lot of people mess up is they forget to square the 25 meters per second. A second area that a lot of people mess up on is they go, when they're putting it into the calculator, they'll go 25 squared divided by 2 times negative 9.8. What might help is to put this in parentheses. Okay, because if you go 25 squared divided by 2 times negative 9.8, the calculator is going to understand as negative 9.8 is being brought up to the numerator. So if you end up getting an error, that's probably one of the two most common things here. Either forgetting to square, or what might help is put this in parentheses, or just take 2 times negative 9.8, which would be negative 19.6. But if you did, when you do all that, you should end up getting a value of about 31.89 meters. Okay, so the units over here becomes meters squared per second squared. The units down here are meters per second squared. So second squares will cancel out, and one of the meters will cancel out, leaves you with the unit of meters, which is what we have down here. So it will reach a height of 31.89 meters. Alright, and we also went ahead and solved for the previous part where, you know, it's going to take it's going to take 2.55 seconds to reach the highest point and 5.1 seconds for it to reach the ground here. So time 0 at 2.55 seconds is at the highest point. Over here, it's going to be a time of 5.1 seconds. So the only thing we're missing now is how far did it travel horizontally. And now, from that information, we have enough information here to solve for what is its range. Let me fold this over so I'm not wasting paper. So let's go ahead and solve for its range. And there's only one form that we need to have here, as your standard velocity is equal to distance over time. So I'm just going to rewrite this over here. Velocity is equal to distance over time. And this is velocity in the x direction, and this is also the distance in the x direction. And we want to solve for the distance in the x direction, so we need to multiply the time out of this. So d sub x is equal to the velocity in the x direction times time. So the range, or d sub x, is equal to the velocity in the horizontal direction, which is 43.3. And the time that it's traveling is 5.1 seconds. So the range of this projectile should be about 220.83 meters. So this will have traveled 220.83 meters. So once again, what we did, kind of review, we had a projectile 50 meters per second, launched at a 30-degree angle. We broke this down into its X and Y components. And then the one that controls how long is it in the air is your vertical components, the 25 meters per second in this case. So you treat it as though a ball being thrown straight up in the air at 25 meters per second. It goes up, its final velocity becomes 0, it's decelerating as it's going up, so it's negative 9.8. Then it starts going to start accelerating on the way back down. While it's going up and down, it's also traveling horizontally at a constant rate of 43.3. So if you know the time for it to go up and come back down, that's also the time for it to travel horizontally. So you find out all the values in this direction here, which will give you how high did it travel, and also what time will it reach the highest point, and what time would it end up hitting the ground. And then using that time when it hits the ground, and since it's moving horizontally at 43.3, and it's moving at a constant velocity, we can then determine what is the range of the ball. So it's the same thing that happens if you are playing, throwing a ball, baseball, softball, football, shot, anything of that sort here. You're throwing a ball or some sort of projectile at a certain angle, at a certain speed, and based upon that, you can actually determine when will it reach the highest point, how high will it reach the highest point, and at what time, and then also where will it land and at what time will it land. And this has been used quite a bit in the study of artillery, and in sports science, anything of that sort here, where any type of projectile will follow this type of pattern here. Again, ignoring wind resistance. But ignoring wind resistance, it's pretty easy to determine where would a projectile travel. So now the next problem is we're going to take this basic information here, and we're going to take this one step further. So let's go ahead and start working this one out.